What I'd like to do is talk a little bit about how we predict durability performance, and I'm going to talk specifically about a thermodynamic model that we've been working on for about the last 5 years. This work is really driven by Keshav, who's our graduate student working on this, and he's working with Professor Isgor and myself. So what we really like to talk about is there's really two primary issues that are facing the concrete construction industry today. One of them is, as you see from this picture from the New York Times, the cement industry is at the center of the climate change debate. One of the reasons for this is you'll hear people quote the fact that 4 to 8% of the world's CO2 comes from cement manufacturing. And while we can debate a lot of things about this statistic, the one thing we can't debate is the fact that we use an enormous amount of cement and concrete in the infrastructure, 10 times more than the next material that we're going to be looking at. The second thing that really is important when we start to think about this is really thinking about the role that the durability and service life play, because this actually also plays very, very heavily into sustainability. So when we start to really think about this and we start to think about what we can really be doing to have a meaningful impact on sustainability and how we design concretes for the next century, we really need to start to look into what changes we need to make and what changes we need to make right now. And I think it's really important that we understand this when we're really talking about mixture designs. Properly designed concrete mixtures that are going to be put into service should be lasting 75 years to a century. So we're making major decisions today, and we need to be investing in those decisions, and we need to be really utilizing the tools that we have. We're suggesting that there's really the need for a three-pronged approach. The first is to reduce the amount of cement clinker that's used in concrete. And a great example of this is the use of Portland limestone cement. We've been really advocating for this over several, now it's going on to decades. And we've seen some major changes with new states adopting this and really moving this forward. We also think that an enormous number of our mixtures are over cemented. So we want to reduce our cementitious content in these systems. And this can be done through optimizing aggregate gradations and using performance specifications. The final leg of the stool is really looking at performance. And there are cases that we've demonstrated where if you use, for example, internally cured concrete, you can triple the service life of your concrete bridge deck by reducing cracking and increasing durability with modest costs. We're looking at about a 3% materials cost, which is about a 1% bridge cost, but we're getting triple the life of that concrete. And that makes a huge difference. And we think the way that we're going to bring in these new tools and we're going to use new industrial byproducts and we're going to create a more sustainable future is by improving how we model these systems. So mathematical and computational models are nothing new to the cement and concrete industry. Ferret, over 125 years ago, defined strength in terms of volume, air, and water. Abrams defined the water to cement ratio. These are nothing more than models that were being used. Powers and Brownyard in the 1940s at PCA developed some very famous models that are the heart of the codes that we use today. And in fact, NIST, with the work of Jeff Fronsdorf, Ed Garbozzi, and Dale Bentz, really led a great effort into virtual concrete. So computational models are really starting to gain acceptance, but we need to see these moving forward into being more than just a scientific curiosity and a scientific industry and a way that we do business every single day. So we want to utilize these foundational works, these fundamental models. We want to use these to enable us to use the material chemistry to predict the overall performance. And I'm going to divide the work into kind of two parts. We're going to talk about equilibrium reactions, and this is sort of classic Gibbs energy minimization types of modeling. And then we're going to talk about the speed of the reaction, which is kinetics, and then talk about how this can be extended to service life. So when we start to talk about thermodynamic modeling of these systems, what we're really talking about is bringing the constituents together. So in a simplest case, this might be water and this might be cement. We need to bring those together, but we're going to need to know about the chemistry of the cement. We're going to need to know how much calcium silicate, how much calcium aluminate, how much calcium ferrite is there. Plus, if we have any industrial byproducts or any SEMs or any other materials, we're going to need to know their chemistries and bring them into the system as well. And we're going to talk much more about this because this has really been the heart of our work for the last 5 or so years. Once we know the chemistries of the material, we need to know their mixture proportions, and we start to bring those into this whole idea of doing thermodynamic modeling and now doing computations on really what is possible to be the reaction products that come out of those systems. So if we think about this, what we're really able to do with the thermodynamic model is we're going to use a technique called Gibbs energy minimization. So the basic idea here is we're going to assume what's the lowest energy state for all the atoms that we have in the system. Let's assume we go to the lowest energy state. What are the reacted products that are going to form? So you can think of this a little bit like trying to do a puzzle. We know what the initial constituent materials are, and what we're looking at is the puzzle of where they fit together the best to get to the lowest energy state. Now, a lot of people will say, well, how do you do this? There's a series of really well-established rules, and these well-established rules are based on thermodynamics and the possible phases that can form. So if we know the possible reactions that can happen, we can determine the reaction products simply by knowing the initial constituents. So if we look at this diagram on our right-hand side, we can look at these phases down here toward the bottom of this graph, the red, the black, and the grayish phases. These are all the cement that we have in the system. These are our A-lights, our B-lights, our aluminates in the system. The aqua color is the water that we have in the system. And if we bring the cement and the water together, we're going to start to form these reaction products. We're going to form calcium silicate hydrate, we're going to form calcium hydroxide, and we're going to form some of the other secondary and tertiary types of reactions that are going on. Now, how we do this is by using this technique that I mentioned called thermodynamic modeling. This is really where Professor Isgor is really driving these models and doing a really phenomenal job, where we can start off by knowing our cement. We can break that down into constituent phases. We add water into that system, and we essentially go through a series of simulations to say, what happens if we predict these as the outputs? What would the energy state be if we predicted this much CSH, this much calcium hydroxide, this much ettringite, right? And we do this over and over again to get to the point where we get to the lowest energy state. And it's actually this lowest energy state that is exactly the composition that we're predicting that we should have for these systems. So once we do that, the really important part is it's not enough just to know the reacted products. We now need to know how those reacted products assemble themselves together. And the real key issue when we start to talk about Portland cements, when we start to talk about concrete, is knowing something about the holes in the concrete or knowing something about the pores. We know there are three types of pores. There's the air voids, which are actually too large to be shown here. There's the capillary voids, which are really the leftover voids left behind by the water to cement ratio. And there's the gel porosity, which is actually part of the glue. And once you know the porosity, and once you know how these pores are distributed, you can start to predict things like strength, transport, shrinkage, and freeze thaw. And this is exactly what we're doing. So what we're doing here is we're taking the Gibbs energy minimization, the thermodynamic modeling. We're saying we have cementitious phases shown here in gray and white. We have the water shown here in aqua, and we predict the reacted products from calcium hydroxide to CSH to monosulfate. And then we actually map those over into a pore space type of a diagram. Now, what I've shown here in this pore space diagram is kind of the classic approach that people have used for cements. And overlaid on that is our model, which is shown here as the red lines. And what you'll notice is that our model matches sort of the classic understanding for ordinary Portland cement very well. And you may say, well, why do we need a model if we're matching this sort of classic case? Well, the classic case is developed for only water and Portland cement. And today's modern systems, we're going to be putting in things other than cement. We're going to be putting in Portland limestone cements. We're going to be putting in fly ashes. We're going to be putting in slags. We're going to be putting in reclaimed or harvested ashes. The value of the thermodynamic modeling is we can bring in any of those materials and run millions and millions of simulations. And when we do that, we're able to start to compare, for example, our predicted porosity versus experimentally measured porosity. And what you'll notice here is they fall very close to a one-to-one line, which means that there's incredibly good predictive capabilities using this approach. We can do the exact same thing now, scaling this up and really going to compressive strength. And what we start to notice is for all of these systems, we're able to predict the compressor strength reasonably well. And the exciting part about this is all of these ashes that are shown here are ashes that are not standard fly ash. They're ashes that are off-spec fly ashes. They don't meet the current specifications. They would currently be landfilled. But what we've been able to show for the Electrical Power Research Institute is that most of these materials, in fact, all of the materials that we tested, could be used to make very good concretes if we simply do the mixture proportioning correct in these systems. We've also been able to use this type of approach to describe some of these new approaches, such as Portland limestone cement, where we can all of a sudden start to take people's fears away and say, really, what's happening when we add limestone into the system? Well, if we look at the right-hand side, what we can notice is if you add limestone, which is our x-axis, right? We look at the pore volumes and the phase volumes that are formed. We see the y-axis. And what we'll notice is the unreacted cement, right? The limestone, the CSH, the calcium hydroxide shown here in green, all of these are relatively constant. We have pore fluid that's relatively constant, chemical shrinkage that's relatively constant. But what we notice is by adding limestone, we get this thing that maybe looks like a Central American flag here. And this thing is really the conversion of monosulfate to hemicarbonate and ettringite. And this actually stabilizes these phases and reduces the porosity in the system. And by reducing the porosity in the system, we can actually increase the strength. So what we're able to do now is explain from first principles why adding limestone initially reduces the porosity and increases the strength. And then when we go to higher levels, we can actually produce the exact same strength that we had originally, but we can do it by producing 12 to 15% less CO2 for the exact same mixture. This is one of the reasons why Portland limestone cement is really picking up and being used so heavily. Further, we can actually start to answer questions that people frequently have, because people say, well, if I start using Portland limestone cement, should I stop using SEMs? And our answer to this question is unequivocally no. Do not stop using your SEMs. Keep using your SEMs. And the reason for this is these SEMs can actually participate in these reactions. So if you have a silicious SEM, silica fume, or a type F fly ash, you see very similar porosity as you would have in the plain case. However, if you have reactive alumina in the system, what you'll notice is that in addition to seeing the benefit of reduced porosity, what you'll see is a further addition because you're stabilizing more of those phases. You see the porosity is further reduced. It's further reduced to a higher limestone content. And then what this carries over into is if we're looking to try to get equivalent performance, we could see that we could be even going to higher and higher limestone contents if we do this. And this is really driving systems like the limestone aluminate calcium systems, like an LC3 system, that is really starting to say these are the directions we should be going, because we can get new reaction products that minimize porosity and give us good long-term strength based on some of these synergies. One of the other things that I think is really important when we start to look at this is we can predict other properties. So we may say, well, how do we know how long it's going to take chloride ions to get to the reinforcing steel? We can actually use the electrical resistivity of the concrete as a measure. More importantly, we use something called the formation factor. The real takeaway here, and I want to just point this out, is that in general, everything that we've tested falls along this 1-to-1 line or slightly better. Now, why is that important? Because an OPC performs exactly the same as a PLC. However, in many cases, the PLC could actually be better. But I think the other thing to really sort of have as a takeaway here, these are your systems that don't have SEMs in them. And you'll notice where your resistivities are. They're kind of in this 1.5 kilo ohm centimeter range. However, if we start to increase the SEMs in the system, we now notice that our resistivity doubles or triples. And by doing this, we've made it 2 or 3 times harder for chloride ions to get through the system. We also notice that we see increased benefits when we have limestone in the system, not because we're decreasing the porosity, but primarily because we're increasing the pore connectivity. We're decreasing the pore connectivity, making it harder for ions to move through the system. So we're actually making smaller and tighter pores in these systems that make it harder for the ions to flow. In addition to this, we've been really looking at people's concern over, with the coal ash industry starting to shrink, what are we going to do for supplementary cementitious materials? And we've really been looking at either off-spec fly ashes or harvested fly ashes or other types of materials that we can be using. Now, as I mentioned, we can take the cement chemistry, we can add in limestone, we could bring in our SEM chemistry, and this could be any SEM that we already use or SEMs of the future. And we can all of a sudden bring these in and start modeling these systems. Now, one of the things that we've tried to demonstrate over the last several years is we need a measure to say how reactive is this SEM that you're bringing in. And we're actually using a test that's been developed, very simple test called the Pozolonic reactivity test. The Pozolonic reactivity test is exactly what the test sounds like. It's measuring how reactive this SEM is. We then add in some kinetics and we're able to go through and produce this type of thermodynamic model that we're talking about. So what is the Pozolonic reactivity test? We're going to take a little bit of alkaline pore solution. So this is going to look like a pore solution and get us up to a pH of about 13.4. We're going to take our SEM, or our industrial byproduct, and use that, and we're going to react it together with calcium hydroxide. And when we do that, we're going to actually produce heat, and we're going to consume some of this calcium hydroxide. Well, if we develop a plot of the heat that's generated on the y-axis versus the calcium hydroxide consumed, we can all of a sudden start to plot out where typical materials behave. And if we look at kind of the pure fundamental lines that we should have on a graph like this, we see this line over here, which is pure silica reaction. This is just silica dioxide reacting with calcium hydroxide. And on this line over here that I'll show sort of as this dashed line, this is the alumina phase reacting with the calcium hydroxide. So now all of a sudden, if we start to plot our data, we can say, well, these points start to fall into this range of about 20 to 30% reactivity, where something like a silica fume up here may be around 80% reactivity. So all of a sudden, we can remove arbitrary assignments of how reactive these materials are and really get things that are really fundamentally based on the chemistry and the amorphous nature of these materials. We can bring in kinetics into this system. We've actually done some work for the Department of Energy to really bring in how we modify these kinetics and have been able to use this to really now start predicting things like the overall porosity and starting to bring in things like the formation factor or the tortuosity. Now, one of the things that we've been really trying to explain to people is the transport properties that we're typically measuring, whether it's through electrical resistivity or rapid chloride, have an error when you vacuum saturate those materials. And that error is these air voids all of a sudden start to become conductive. But even with this error, we're able to predict this very well based on first principles. So the model prediction here is not a curve fit. It's not anything like that. It's really saying, I started off with these chemistries. I've now predicted the porosity and I've predicted how connected these pores are. And all of a sudden, I can now predict how fast ions are going to be moving through the concrete. So I can get a diffusion coefficient. I can then start to predict how many of these ions are going to bind to the system as they start to move through the system. So what you'll notice here is the black are the actual experimental data that we've actually measured, and the red is completely simulated data saying if we know what the chemistry of the system is and we know some basic rules or some basic principles on the binding that should take place, this is what we would predict from the red in the red lines. So what I would take away here is if we can predict the diffusion coefficient and we can predict the binding coefficient, all of a sudden we can now start to predict some of these complicated chloride ingress profiles. And we're doing this all before we've ever had to even make a concrete. So one of the huge advantages of this type of approach is we can do this for millions and millions of concretes and predict these reactive transport models and start to now predict things like how long will my concrete last in corrosion? How long will my concrete last when it's exposed to de-icing salts? So I can go through and I can say, I've got a pavement. I have to design it for de-icing salts. How do I design this material? Well, I focus in on minimizing the calcium hydroxide in the system. The way that I do that is I use more and more SEMs. By using those SEMs, I reduce the amount of calcium hydroxide by diluting the cement that's in the system, but I also get this Pozolonic reaction that's taking place. And now I can actually design my system with the right amount of SEMs so that it has a long-term durability. I can then start to take this type of approach and I can apply it to different types of things that we would be designing for. So for example, if we did this for a pavement in the Midwest, we may say we need to have a certain strength, we need to have a certain transport property, we need to minimize the amount of calcium hydroxide to minimize salt damage. We may be looking at pH to work on ASR, and then we look at time to critical saturation because this is going to be related to the freestyle performance. And I can establish all these performance criteria and then say, let's go through and predict the concretes that would meet these particular performance criteria. So I have a certain SCM available, I have a certain cement available. I can start to go through and I can make these concretes. And what I can start to do is make these sorts of plots. So the idea here is I can say I've got water to cement ratio along my x-axis, water to binder ratio. I've got the amount of SCM along the y-axis, and each one of these contour lines is a specific property. 20 MPa strength, 25 MPa, 30 MPa. So if my criteria is 30 megapascals, everything below this line is a feasible concrete for me to be manufacturing. I can do the same thing when I start to look at the transport properties, and now everything below this red line is something that's worth manufacturing. I can continue this over and look at freestall performance, which is everything below the blue line. And then if I look at the calcium hydroxide, it's actually everything above this green line. So what this really helps me to do now is I've considered a huge range of potential mix designs, but I've been able to focus in on the region that makes the most sense and the likeliest set of mixture proportions that are going to meet my specific design criteria. And I can do this for any design criteria and really start optimizing the systems that we're designing, the amount of SCMs that we have in the system, and the carbon footprint of our concrete. So in summary, we've talked about several different innovations, but we really need to take these innovations to something that can scale. And this is really why we're focused in on things like Portland limestone cement, why we're focused in on better utilization of SCMs. And the reason is because we need to start utilizing these materials much, much faster. We need to start moving away from empirically based mixture design and trial and error and really start using something where we're really taking advantage of computational power. We've talked here about using computational approaches to move away from trial and error and to really start to accelerate change to design mixtures with a particular SCM content. We've talked about using the Pozolonic reactivity test. This is a test that we think can replace a lot of the empirical tests that are out there to really help us bring in both commercial SCMs that we're using today, as well as new and emerging SCMs. And we really think that testing can be quite beneficial, but we need to use these materials to get us to the point where we're designing our experiments much, much better and reducing the overall cost of designing these mixtures. We talked recently with a producer who started to bring a new cement online. They said the cost of bringing that new cement online just from mixture trials was around $1.2 million. By using an approach like this, they believe they could have cut that cost by 50 to 65% to really focus in on the cement chemistries that would have been the most beneficial for them to look at from the beginning. So with that, I will turn it back over for questions. I've really enjoyed being with you today and look forward to a time where we can be together in person again.
Well, thank you, Professor Weiss. That was very interesting presentation, and I can see the value of your sustainability triangle. In fact, we're very fortunate today to have the speakers who covered basically everything about civil engineering materials from atoms to full-scale pavement. I'll have a time for a couple of questions. In fact, we have 3 minutes, so I'd like to invite questions from the audience.
Well, let me start probably just to initiate the conversation. I guess on slide 11. Well, by the way, very interesting presentation and very informative. Slide 11, the thermodynamic modeling. I was a little bit confused because does this assume that the materials, especially supplementary cementitious materials, have 100% reactivity, or?
No, this is actually, so that's actually a great question. And if you would have asked this question 6 or 7 years ago, the entire field was assuming that when you put the SEMs in, they were 100% reactive, which is about 70% of the wrong answer, right? These materials in general, a fly ash is generally about 20 to 40% reactive. And this is really where we bring in this idea of this test that I mentioned here, this Pozolonic reactivity test, because all of a sudden now what we can do is we can say, you have a particular SEM, maybe it's this SEM that's shown down here in red. This has a reactivity of 25%. The other 75% is inert material that's never going to react. So we can actually build that into the system and get much, much more accurate measurements by doing this, because we're actually considering those reactivities. So this is a really important question, and I think really highlights a lot of the changes that are taking place in the industry over the last several years.
Thank you, Dr. Weiss. So is this test standardized?
So we were on a discussion yesterday with different people on the standardization committees. They are spending lots of time talking about how to standardize tests. We do this test. Typically, we've got a written up standard that's for us. Whether ASTM accepts it or not, I'm not going to spend time debating this at ASTM. We're going to continue moving forward because we need this as a model input, and we think it's a very, very clever way to measure the behavior of the system. There are lots of people who want to say, well, it's about the amorphous or glass content. This, for example, where you fall on this graph, and we've shown this before, is a great indicator of your glass to amorphous content. There's lots of other people who want to say, well, what if you have some calcium? We've got equations that account for these. And in fact, in January in Concrete International, we're going to have an article that really says you could greatly simplify a lot of the testing that we do for fly ashes simply by measuring the heat and using a graph like we see on the right-hand side. So this is something we believe in very strongly. We've presented it to ASTM. If they want to move it forward, great. If they want to continue debating other things, that's great as well. We're moving forward with this.